learning algorithms, especially deep neural networks, have become important analysis tools for many different domains, from finance to healthcare to gaming and more. That is because of their better or similar performance of doing tasks compared to human beings. However, there are a couple of challenges that machine learning algorithms, particularly deep neural networks, deal with. These models are huge and need billions of operations per task, and also they require a lot of parameters to train. Also, they are complex to understand and tune, and it gets worse when it comes to heterogeneous kind of data consisting of text, images, etc. They need a lot of data and iterations to train to get a good accuracy. And also, they are highly vulnerable to error and noise, especially hardware noise. So to this day, the best cognitive tools that we have are our brains. So if we think about the game that took place between OpenAI 5 and those are two world champions, in order for the OpenAI 5 to defeat these world champions or perform similarly to them, it took it thousands of CPU cores, dozens of GPU cores, and of course, dozens of scientists. However, it took the world champions probably a coffee or a sandwich and, of course, a brain. However, we cannot really even loosely mimic the brain. But hyperdimensional computing, similar to brain, is based on neural representation of data. And it has a couple of characteristics that makes it a suitable choice for IoT scale devices. First of all, it is lightweight. It has a very small model and simple computations. It is very easy to understand and calibrate for different kinds of data. It is very energy efficient, has a low power consumption, and gets a good accuracy after a few epochs of training. And also, when it comes to robustness, it is highly tolerant against noise and error, and therefore we can use it in unreliable but inexpensive hardware and communication. Hyperdimensional computing, in a nutshell, consists of basically three main steps of encoding, training, and inference. In the encoding phase, we get the input data and we encode it into a hypervector of usually 2K to 10K dimensions. And when it comes to training, all of the samples that belong to the same label are accumulated or superimposed together to create the classes that correspond to a particular label, for instance, cat class or dog class. Then when it comes to inference, the query data is encoded to a query hypervector, the same method we did for the training data, and then its similarity with either of the class hypervectors is calculated, and whichever class which is more similar to the encoded query is the class that it will be labeled as. Hyperdimensional computing has been used in many different domains and different types of classification, clustering, regression, and more. And also it has been implemented on all the different kinds of data, from images, time series, text, graphs, and more. However, there are some challenges that are also associated with hyperdimensional computing. The first challenge is its accuracy efficiency trade-off. So in the right plot, you can see how the accuracy changes when vector length changes on a couple of benchmark data sets. And in order to get a high accuracy, we need to have a high dimensional vector. Also, if we consider traditional hyperdimensional computing, it has low accuracy on complex data like image data. So in the right, you can see the accuracy that we gain using a shallow CNN and hyperdimensional computing on 10 different data sets and their average. And you can see that HDC yields 26% lower accuracy than a shallow CNN. Also, there are privacy and security challenges that are associated with HD. So in terms of privacy, data can be easily reconstructed from hypervectors. So if you take a look at the image on the right, you can see the original images and the reconstructed images by using some related works that we'll discuss later. And you can see that the reconstructed images are have a pretty good quality. Also, another issue with hyperdimensional computing is that it's susceptible to adversarial attacks, and you can perturb its accuracy with small perturbation in input data. And this is actually our future work. Also, there have been works that try to increase the accuracy of hyperdimensional computing using CNN feature extraction. They have low efficiency because the overall system efficiency will be still governed by CNN component. So our contributions here are twofold. In the first work, we try to improve the efficiency while yielding similar accuracy to the state-of-the-art and even outperforming it. And in the first work that was presented in ASP-DAC, instead of using a randomly initialized projection matrix to learn the encoding, we use a simple neural network in order to learn these parameters and then use these parameters for encoding. And the second work, we will mainly focus on improving the accuracy on image datasets while preserving the privacy. And the second work, I will discuss it later. About the previous works that try to address the accuracy efficiency trade-off, we can categorize them into three main categories. The first set of works are the ones that try to propose novel encoding and training. For instance, more complex encoding like nonlinear encoding, dimensionality reduction using isometric mapping, updating the classes based on a particular weight, or window-based encoding, but they have more complex operations and a high number of operations. And also, when it comes to quantization and dimensionality reduction, they have low accuracy. The second category of works are the ones that try to use classical feature extraction, like a stochastic Eschi-like arithmetic histogram of gradients, but the feature extraction will become a bottleneck there. And also, these methods would also have low accuracy under quantization and dimensionality reduction. And also, in comparison to neural network, they have subpar performance. The third category of related works are the ones that try to leverage neural networks. So they model HDC as a neural network to learn the classes, but they have complex training and backpropagation, and also they are not suitable for in-field learning. So the classes that are learned by these models, we cannot use them in the scenarios like lifelong learning, because we cannot update the floating point classes that we have observed and then accumulate them with new data. There's another set of works that try to use feature extraction using convolutional neural networks or other NN-based methods, which I will discuss in the second work. So in our work, we use neural network to boost the accuracy of HD, but instead of learning the classes in the previous work, which has its own problems that we discussed, we learn the parameters of the projection matrix, and then we use them as our projection matrix instead of the randomly initialized projection matrix. And then we do the encoding the same way we did in the conventional HDC. And also the training is also done the same way that we did in the conventional HDC. So here we show how the projection-based encoding is done. So if we consider an image, for instance, here, we take each of its pixels, and each of them will be multiplied by a hypervector of 2K to 10K usually. And then after they are multiplied, we sum all of the elements up. And then the summation would be, the summed hypervector will be binarized and will represent the image. And if you think about it, it's basically like vector matrix multiplication, where the vector is our feature vector, and the matrix is our projection matrix, and the result is our hypervector. So each of the indices of the hypervector, hi, is basically created using multiplication of the feature vector times the i's column of the projection matrix. And each of the elements of the projection matrix are randomly initialized as -1 or +1. So in order to create each hi, we are basically giving each of the features in our sample a weight of -1 or +1. But there should be a better approach and wiser approach rather than randomly initializing this projection matrix. And that is our inspiration for our method. So we propose Pioneer, in which we deploy HTC as a 2-layer neural network and use the learn base for initializing the projection matrix. So I would like to explain more how it mathematically makes sense that we learn the parameters here would work in our HTC in the future. So if we consider, so the inputs are our feature vectors in this binary, in this two-layer neural network, and then the hidden nodes are our each of the indices of the hypervector. And each of the hi is basically, as we discussed, the multiplication of the i's column of the projection matrix and the feature vector. And also, each of the output nodes is multiplication of the hypervector and class Cj. So Cj is basically shows the similarity of the hypervector and class Cj. And here I won't go over the mathematics, but if we use cross entropy loss function, we can observe that how the class parameters are updated. So when the label is, for example, C1, so Y1 is equal to 1, we can observe that each of the elements of class C1 will be added by a proportion of the hypervector with index I. And then when for any other class that is not class 1, a coefficient of that hi will be subtracted from the class value. So updates in class hypervectors in the above neural network aligns with HTC class updates, because in HTC also, when the hypervector is similar to a class, we just add it to the class it corresponds to, and then we subtract it from the class that it's it doesn't belong to. So here we show T-distributed stochastic neighbor embedding dimensional reduction. So we show the in the left we have the hypervectors that are generated using Gaussian projection matrix, and the right one are the ones that are generated using our learned projection. And you can observe that Pioneer learns to distinguish classes better than using a randomly initialized projection matrix. Also, here in the right, we show the distribution of the learned matrix elements for MNIST datasets, a speech dataset, and a Gaussian. And you can observe that Pioneer basically learns the parameters that are learned are based on the characteristics of each of the datasets, and it is different from the Gaussian distribution. So here we show the projection matrix that is learned, and you can observe that it has big D by small d dimensions, where big D is usually 2K to 10K, and a small d is, for instance, for MNIST is 784 dimensions, and it's pretty large. So in order to be more efficient, we could do quantization. So if we do quantization using 4-bit quantization or 1-bit quantization, we are capable of storing a lot of memory and computations. But still, even when we are doing quantization with 1-bit, we need to store big D by small d by the value, 1-bit for the value. And this is pretty huge. So in order to be more efficient, we propose a sparsification. However, we first need to discuss the conventional specification that is used, and we will describe how ours is doing better. So this is matrix level sparsification, which is not hardware efficient. So what it does is that it takes the highest magnitude ratios of a ratio of highest magnitude values of the projection matrix and binarize them and set the rest of the matrix to be 0. But in order to store the non-zero elements here, we need to store the column index, the row index, and also the value. However, we propose a row sparse sparsification. So what we do is we select k largest magnitude of each of the rows, and we show that this yields minimal discrepancy to encoding output. And also, we do not need to store row information. Because, for instance, here, when the number of columns D is equal to 8 and our sparsification is equal to 75%, and we are storing 2 non-zero elements in each of the rows, we know that the first 2 elements are belong to the first row, the second 2 elements belong to the second row, etc., etc. So also, another issue that we are trying to solve, and we could observe in matrix level sparsification, was that it could happen in matrix level sparsification that for a particular row, all of the elements are set to 0 or it's highly sparsified. So for a particular sample, all of these features would be given 0 weights, which is not what we want. So here we show the how the encoding bit change when the sparsity changes, and we show it for matrix sparsity and row sparsity. And we can observe that when the sparsity increases, the amount that encoding bit change compared to the ideal encoding is lower for row sparsity. Also, we show the accuracy for MS dataset when we do a matrix sparsification and row sparsification, and we can observe that after some point, after some sparsification ratio, it is while matrix sparsity is lowering the accuracy, row sparsity is not, it's actually increasing it. And we believe that, we think that the reason behind that is that the sparsification acts like a dropout, and it impedes overfitting, and that's the reason we are getting good accuracy even though we are sparsifying. So the total number of bits that are needed to store the non-zero elements are big D times small d times 1 minus the sparsification times, these are the number of elements that are non-zero when we are doing a sparsification with a sparsity rate of S, times the number of bits that are required to store each of the non-zero elements. So we need 1 bit for storing the element of that, and also log of D for storing the column. So as we discussed, we don't need to store the number of rows. And in the plot, we can see how the matrix size changes when the sparsity increases. For MS and UCR datasets, we can see that after a while, MS at 91% and UCR at 83% start to compensate the index overhead and save memory. So we use FPGA as our architecture because of its customizable bit width for operations and memory, less data movement, balance is balanced for resource usage and power. And we show the data bus for generating 1 encoding element. I will discuss it in the next slide in more detail. So in each cycle, 1 non-zero value of projection matrix is processed as the following. So if we consider the projection matrix that we have learned, we have a sparsified and we have binarized as shown here. And the sparsification rate is 75%. So we have the number of columns is 8, and we have 2 elements that are non-zero in each of the rows. In order to store them, we have a projection memory that, for instance, the first one has a column index of 1, and the last one in the first row has a index of column index of 7, and their value are -1 and +1. We also have feature memory, and in order to do the multiplication of the feature memory and the first row, we would what we need to do is just adding or subtracting the corresponding elements of the features that are not that the corresponding indices in the row are not 0 there. So here, feature 1 and feature 7. And then we can see that in cycle 1, we will be calculating, we will be updating the first index of the hypervector with the first value, and then in cycle 2, we will be updating it with the second value of the row. And then in cycle 3, once we are done with the first row, we move to the second row, and also at the same time, we will preserve the similarity score of the hypervector element that we just generated and the corresponding class element in the score memory. So in terms of experimental setup, we worked on, we deployed our method on 6 different data sets: CFAR10, FACE, Isolate, MNIST, PAMA2, and UCR. And for baseline comparison, we use binary random projection, dual nonlinear encoding, online HD, mani HD, LHTC, random Fourier feature, and DNN. We need to mention that we are within the scope of IoT scale datasets, and we are trying to improve the efficiency on these datasets. So here we show the accuracy results on multi-epoch and single epoch of training for all the different datasets, for all the different models. And while our main goal is not increasing the accuracy, we can observe that the accuracy is by up to 1 or 2% higher than the best baseline HDC when we use Pioneer. And also, in comparison to DNN, we only have 1.22% drop when we are doing multi-epoch of training. But when it comes to single epoch of training, we are getting a higher accuracy than DNN by 15.6%. So in terms of efficiency, we show the down scalability results of our method. The plots in the left show both of them. The first one shows the accuracy with different vector sizes when our projection matrix was quantized by 4-bit. And then the right one shows how the accuracy changes with different vector sizes when the projection matrix was binarized. And we can observe that at a small dimension of 100, Pioneer with in4 achieves an average accuracy of 95.61%, which is only less than 1% drop versus when we use the dimension of 10K. Also, in the right, we show the average accuracy of different models with different vector sizes. And the black one, black and gray ones are ours with in4 and binary quantization. And we can observe that our method can get a higher accuracy even in very small dimensions. For instance, at d equal to 50, Pioneer achieves 26% higher accuracy over randomly initialized projection that emphasizes the importance of learned projection. So here we show the efficiency results, time and energy consumption for different data sets. And we compare binary random projection, nonlinear, DNN, and our proposed method. And we can observe that Pioneer achieves faster inference time by up to 180 times versus the best HTC-based method. And also in terms of energy consumption, in comparison to the best HTC model is doing 165 times more energy saving.